Okay, so for both of these here, guys, I mean, one's kind of a work energy theorem / conservation of energy question, and obviously number 2 is strictly conservation of energy. All right. How do I know that number 1 is got work energy theorem involved in it? It asks, A, how much work is done, always a good sign. Okay. Secondly, one of the givens is something I never get in a law of conservation of energy question. Well, I might get mass, okay? But, sorry, one of the things I'm asked to get, sorry, not a given, is never given to me in a law of conservation of energy question, and that's force, right? Okay, so when you're looking at your exam next week on Tuesday, okay, sometimes it gets tough to tell the difference between a work energy theorem question and a law of conservation of energy question. Look at what you're given. You know, in a law of conservation of energy question, the only force acting is gravity, so it never talks about force. Okay, if a question says force gives you force, asks for force, it's a work energy theorem question. Okay, because sometimes they have a lot of stuff in common. They might have 2 speeds, they might have 2 heights. Okay, and they both kind of share those, and so as a result they can get confusing. Okay, the thing that's the determining factor would be if the question says determine the work, okay, or it gives you force. Okay, so look for those 2 things to help you tell them apart. Because, I mean, right now you're probably going, come on, I know how to tell those apart. Today, yeah, you do. Okay, but Tuesday, it's an exam, you're a little more stressed, yeah, we don't always think quite as well. Okay, they just know that that's kind of a little thing that can help you out. All right, so for question number 1 here, okay, our givens are mass, 1.5 kilograms, initial speed, 3 meters per second, final speed, 9 meters per second. All right, we know it's a work energy theorem question, but they get a mark for givens and a mark for identifying it as a law of conservation of energy question. All right, since it only asks us to find work, I don't even have to do the force times distance thing, do I? I just need to remember that work is a change in energy. All right, so I'm looking at my formula here. I've got kinetic energy that's changing, so final kinetic minus initial kinetic, 1/2 mvf minus 1/2 mvi squared. Okay, give them a mark if they got to that point. Okay, and then, excuse me, they've got, okay, to plug in the numbers, 1/2 times the mass, 1.5 times the final speed, 9 squared, minus 1/2 times 1.5 times 3 squared. When we do that, we should get a final answer of 54 joules. So everywhere where you see a circled little 1, they get a mark. The whole thing is out of 5. Okay, make sure they have units on there. In this case, it should not be negative because 9, the final kinetic is greater than the initial kinetic. So no, they won't get that one right, unfortunately. Then it's wrong because newtons are a unit for force, not for energy. Any other questions there, guys? Okay. And guys, that's honestly, that's a very common mistake. If there's a thing that costs people marks needlessly, it's confusing newtons and joules. Okay, newtons are for force, joules are for work and energy. Okay, make sure you keep them straight. Okay, so our roller coaster, okay, starts at the top of the 35-meter hill, traveling at an unknown speed. Okay, later in the ride, the coaster is 12 meters off the ground. It's traveling at 21.8 meters per second. How fast was it going at the top of the hill? So we're looking for initial velocity or initial speed on this one. Okay, we're told the initial height, we're told the final height, we're told the final velocity. So give them 1 for their givens. Maybe they made their givens in the form of a picture, which would be fine. Okay, all right. The thing we know here is that the mechanical energy at the top of the hill is the same as the mechanical energy at the top of this little hill. All right, why do we know that? Because there's no mention of work being done anywhere in the question. All right, so give them a mark if they had EI equals EF. Okay, because they recognize that as a law of conservation of energy question. Okay, we'll give them a mark for plugging the formulas in all the way. Okay, that would be mghi, or maybe they didn't even bother writing in the mass. Maybe they went straight to this second line, ghi plus 1/2 vi squared equals ghf. Okay, whichever. Okay, give them a mark kind of for this step here. Okay, a mark for that step there. All right, and then for manipulation, okay, we got to solve for vi. So to solve for vi, I've got to subtract ghi over to the other side, and then I've got to divide by 1/2, and then I have to square root because vi is squared. All right, so give them a mark if they got to this manipulation, ghf plus 1/2 vf squared minus ghi over 1/2. They're going to have another mark for plugging the numbers in the right places. Okay, 9.81 times 12 plus 1/2 of 21.8 squared minus 9.81 times 35 over 1/2 should give us 4.9 meters per second. Okay, so that one is out of 6. Okay, and I told you that on a test, probably a law of conservation of energy question would be out of 6 to 8 marks. Okay, depending on how generous I feel when I decide what it's out of. Okay, I think the one on your test might be out of 7. Okay, everybody with me there? All right, how are we feeling about this law of conservation of energy stuff? Okay, are they all pretty much the same? Yeah, really they are. Okay, all right, so give them a mark out of 11. Let them see it. Make sure your name is on it before you hand it in, please. All right, so we've been talking about work energy theorem, we've been talking about law of conservation of energy, and certainly those are the big mark type of concepts for this unit exam. Okay? But efficiency is also an important idea. Not so much, I mean, unfortunately, marks-wise on the test, it's not nearly weighted as heavily as the others, but, okay, it's still something that's important because it's how we can, let's say, better use our resources. Okay? We do a lot of things in our society that are incredibly inefficient. We use a lot of procedures and methods of generating power that are ridiculously inefficient because they're cheap and easy. Okay? Now, what we have to look at if we want to be responsible, okay, with our resources is how can we increase the efficiency of those things? Now, in the laws of thermodynamics that we talked about earlier, okay, we said that every time energy is converted from one form to another, some energy is lost. Okay? So the more steps you have between your initial source of energy and your final source of energy, the less efficient that process is going to be. All right? So if you consider, let's say, how we generate electricity, for example. Okay? How do we generate electricity in Alberta? Right. Over 90% of all electricity in Alberta is coal generated. Okay? We like to kid ourselves that we have these big windmills in one place in the whole province and they generate so much electricity. They represent less than 5% of the grid. Okay? They're nice, but there are not that many of them. Okay? So most of it is coal because it's cheap and it's easy and there's lots of it. Okay? When you burn coal to make electricity, first, you take potential chemical energy in coal. And when you start it on fire, it turns into what? Heat. It turns into thermal energy. Thermal energy is the least efficient way to make any other kind of energy. Okay? Because heat easily flows from hot to cold. And everywhere else is colder than the boiler, okay, of a coal-fired generating plant. All right, so you're always losing energy. I mean, you can see that when you drive past a coal plant. You can see just how much steam is coming out of the stacks. All right, if you've ever taken Stony Trail up to Cross Iron Mills, okay, you go by that big plant there that's got the two big round stacks, and is there always steam pouring out of those things? Okay, that's a lot of heat, right? Not all of that heat is being used to generate electricity. Most of it is being lost. Okay? So we get this heat, and we use that heat to turn water into steam. Is that another energy conversion? Yeah, we're trying to take heat and turn it back into kinetic energy of moving molecules. Okay? Those moving molecules eventually move fast enough that they change state. Okay? That is, they move further apart, they become a gas. The gas takes up more space, and so it rushes through pipes, okay, and turns turbines, which are kind of like a fan. Okay? They're a glorified fan. And when the steam goes through those fans, those turbines, they turn. Okay? And those turbines are connected to a generator. So we've got chemical energy to thermal energy to kinetic energy, kinetic to potential in the changing of state. Okay, then we have again back to kinetic with the steam moving through the pipes. Then that's got to turn a turbine. The turbine's connected to a generator which has to turn, and the generator can make electricity. That's a lot of steps, right? And at every step, energy is lost. Every step, energy is lost. Okay? It's not a great way to make electricity, but it's cheap and easy, and we have lots of coal in Alberta to do it with. So that's how we do it, because that keeps energy prices low. Okay? So we don't have gigantic power bills. That's good for us. Okay? Everyone with me there? Okay? But it's not very efficient. Now, if we're looking at something we use every day, okay? Something we use every day other than electricity, it'd be your car. How efficient do you suppose your car is? You know, if it was 20, if every car was 20, we would use a lot less fuel. The reality of it is, most cars are not even 20. Okay? Because what are they they're turning chemical potential energy in gasoline into what? Right off the bat, the first change is chemical potential into heat. Okay? It's the first change. Over a third of the energy in your fuel is actually used to run the cooling system of your car to keep the car from melting down. That's how inefficient the processes are. Okay? Now, that's just the initial conversion of chemical energy to heat. Okay? When that heat happens, that thermal energy happens, there's the expanding gases inside the cylinder of your car. Okay? And the expanding gases take up more space. They push the piston down. That's the drive phase. We talked about that, right? Okay, the power stroke. Okay, we talked about that earlier. That's where sort of the power for your car comes from. Okay? But pistons are metal. The engine parts they sit in are metal. Metal on metal is very high in friction. Okay? So is more heat generated there? Yeah, that's why you have oil in your car. Okay? The oil helps to reduce the friction so that your car's parts don't expand so much that they can't move within the cylinder of the car. When that happens, your engine seizes. Okay? That means basically the rods that connect the piston to the drivetrain snap because the pistons can't move. Okay? Everyone follow me there? It's very bad. When the oil light comes on in your car, stop. Stop right away. Okay? Because by the time that oil light comes on, your car is already in really big trouble. Okay? It's already lost a lot of oil. Right? So you don't want to be driving past that because your car is that inefficient. It's always generating heat. Okay? Is heat helping drive the car forward? No. So that energy, none of it is doing useful work. Okay? Very little of it is actually driving the car forward. So if we look at this here, okay, in your car, your exhaust system gets rid of some of the heat, a third of it. Okay? A third of the energy used in your fuel, okay, goes right out the exhaust pipe without doing any useful work. Okay? Another 33% of the energy in your fuel is used to drive the water pump and the cooling system, you know, through pushing coolant through the radiator and keeping your engine from melting down. Okay? The drivetrain, that is all the moving parts. Okay? The friction within those moving parts uses 10% of the fuel in your car. Have you moved forward yet? No. Okay? We're at 60, 77, 70, 76%, and we haven't moved forward yet. Okay? Then you got your accessories. That's your power windows, power door locks, heater, air conditioning would probably be included in that. Your stereo, okay, if you have like a really big thumping stereo that people can hear from 2 blocks away, it's probably a bigger number than that because you probably have more than one amplifier and maybe a separate alternator to run your stereo. Okay, so that's 4%. Okay, internal friction, that would be not in the engine now. We're talking about within, let's say, you know, the rear end or the front wheel drive, things like that. Okay, is another 6%. Here's what's left. 14%. And this is for a passenger vehicle, mid-size passenger vehicle. So let's say a Honda Accord, okay? Or a Chevy Malibu, or a Ford Taurus, okay? Something along those lines. A average size, maybe 4, maybe 6-cylinder passenger car, all right? Not a minivan, certainly not a truck, okay? Those numbers, the bigger your vehicle gets, they go down. All right? Now, obviously, we're making cars more and more efficient, okay? They are getting better, right? But they still all rely on basically the same idea. Now, what if you have a hybrid car? Is that more efficient? It is. A hybrid car is more efficient. A hybrid car will probably run more than 20% efficiency. Okay? Because it has an electric motor that can assist. All right, now the electric motor, the battery that powers it, where does it get the power from? Right. Well, if you have a plug-in hybrid, okay? Most hybrids are not plug-in hybrids. The battery is charged by burning gasoline and running the engine to power the alternator which charges the batteries. Okay? Now that may seem ridiculous, but actually it's more efficient to do that than it is to have the car under load all the time. So, in a hybrid vehicle, okay, what you have is two motors. Okay? A hybrid car is primarily a gasoline-powered vehicle. The electric motor only kicks in under load. Okay? So if you're going uphill, the electric motor will kick in, okay, and assist the gas engine going up the hill. When you're pulling away from a stoplight and you're accelerating and the engine has to work harder, that's when the electric motor kicks in. Right? When you're driving on the highway, maintaining a constant speed on a flat stretch of road, your car is running entirely on gasoline. All right? So a lot of people, they unfortunately don't understand that, and they buy a hybrid vehicle for the wrong reasons. They think, you know, let's say if they're driving from, let's say, High River to Okotoks every day. It's all highway, right? There's barely any lights to do that. Okay? They bought a hybrid car for the wrong reason. They're not getting anything out of it. A hybrid car gives you the most benefits in stop and go traffic when the electric motor can kick in more often. Okay? And in fact, in a lot of hybrid vehicles, if you're just sitting in stop and go traffic, the gasoline motor also shuts off. So you can actually sit in your car and the engine isn't running. Okay? Then when you press the gas pedal, the engine fires up again. Okay? Or if you've been sitting for a while and you've had your accessories on, the engine will fire up, charge the battery because you've drawn too much from it. Okay? So is that going to save fuel? Yeah, and it's going to be more efficient because an electric motor is way more efficient than an internal combustion engine, right? Because in an electric motor, there's way less contact between parts. Okay? Anytime you have contact between moving parts, you have friction, that reduces efficiency. Okay? But in an electric motor, you've got magnets, okay? And the magnets oppose each other, and essentially, the inside of the electric motor almost never touches the rest of the motor. The magnets just change their polarity and force the motor around. You guys remember building that in grade 9? I think you have to do that in grade 9, right? You don't do that anymore? Okay. All right. Anyway, you used to have to build an electric motor. Okay, but that's how they work. All right, which is why an electric motor is way more efficient, okay, than a gasoline-powered engine. And that's why big naval vessels like nuclear submarines, okay, and things like that, they run their propellers are actually run by large electric motors. Okay, because it's more efficient than gas, and you can't burn gasoline when you're underwater. Why not? No oxygen, yeah. It's hard to run an internal combustion engine underwater. Don't try that. Don't drive your car underwater. Okay. They would run the diesel, they'd have to surface. Yeah, so in World War II, yeah, all the subs were diesel-electric hybrids, actually. Okay, that's where the idea for hybrid cars came from, is from old submarines. They were diesel-electric hybrids. So you'd surface, run the diesel-charged batteries, go underneath, run on electric power for as long as you could, surface, run the diesel. Okay. Now, you could run the diesel for short periods under, okay, but it used the oxygen that the crew required to breathe, so you didn't do it very often. Okay. If you needed a lot of speed, you surfaced and fired up the diesel and, yeah, ran like hell. Okay. All right. So it gives you some idea here, guys. Just, you know, we take this for granted. We accept this efficiency. Okay? Would you go to the doctor if he was only right 14% of the time? I wouldn't. Okay? We kind of have expectations that, you know, 14% is not very good, but we accept it every single day when we step in the car. Okay? We accept it every single day. Okay? Something to think about. All right. So, efficiency, guys, is the percentage, essentially, of your input energy that is actually doing useful work. All right, so if we want to calculate efficiency, all we do is divide the useful work that was done by how much energy we had to put in. And when we do that, we get a decimal, which we multiply by 100. Okay, in the same way that when you calculate what percentage you got on a lab or a test, you take what you got divided by how much you could have got, and there you go, you've got your percentage. Everybody follow me there? So these are easy calculations, right? All we got to be able to do is tell which one's the input work and which one's the useful or output work. Now, is there going to be an easy way to tell them apart? Output is always going to be the smaller number because no energy conversion is 100% efficient. The larger number will always be the energy you had to put in. All right, does that sort of make sense? Okay. All right, so like we said here, systems with moving parts always lose some energy as heat, okay, which is consistent with the laws of thermodynamics we talked about before, okay? When you do work on a system, that energy is always present. Energy can't be created or destroyed. That's the first law of thermodynamics. It's the law of conservation of energy, okay? The second law of thermodynamics says that energy always flows from hot to cold, yeah, high to low, all right? And that's what's going on here, okay? Whenever you have mechanical parts moving past each other, heat will be generated and the heat will flow away out of the system doing no useful work. All right, energy supplied to your body by food, okay, must equal all of the energy and useful work done plus all the wasted energy, which includes heat and whatever, okay? According to the second law, heat flows from hot to cold during that process. If we could get something in there, okay, we could harness that heat. Agreed? Right? That wasted energy that's going away. If we could get something in there, like a heat engine, remember we talked about that kind of the first day, we could harness that heat to do some useful work. Well, car manufacturers have figured out a way to do that. And on many hybrid vehicles, Cameron, okay, on many hybrid vehicles, they've put thermocouples into the brake rotors. Okay? Anyone remember what a thermocouple is? Okay? Thermocouple is that device that turns heat directly into electricity. All right. So what they did is they embedded these in the rotors of the brakes. So in case you don't know what I'm talking about, okay, on modern cars you have what are called disc brakes. Okay, so you have a big circle which you can usually see through the wheel. Okay, it's kind of shiny, and then there's these clamps. Okay, those are the brake pads. Okay, your car squeezes the brake pads against the rotor, and that's how you stop. Now that generates a lot of heat. So what's been done is they embed thermocouples all through the brake rotors, and they connect them to the batteries. So when you slam on the brakes, okay, the heat that's generated by stopping, some of it, not all of it, but some of it, is returned to the batteries. Okay, is that making good use of your energy? Yeah, because otherwise, every time you stop, all the kinetic energy you built up by burning fuel gets turned into heat and given to the environment. Okay, which is not very useful. Mm-hmm. Right. Yeah. Yeah. It uses the kinetic energy. It almost. Yeah. The brake is almost within the drivetrain, right? It's kind of like yeah. Right. Yeah. So it squeezes the wheel against there. Yeah. Yep. So there's ways obviously to make better use of the energy we have. Unfortunately, that stuff doesn't usually come cheap. Okay. Now, does it in the long run? Are you using a lot less energy, and then as a result, does it pay for itself? That's kind of the balance point, right? Okay. If you have a plug-in hybrid, yes, you're not spending money on gas. You're spending it on electricity. Okay. The energy to get to work has to come from somewhere. Okay. You're buying an electric car doesn't mean you're getting to work for free. Okay. Your power bill is going to go up a lot. Electric motors are a lot more efficient, yes. There's no question about it. An electric motor is more efficient than an internal combustion engine. The problem is where you get that energy from, right? You still have to put energy into your car to get to work. You might use less because you're running a more efficient vehicle, okay? But you're still using energy to get to work, right? It depends. Right now, probably not. Price of oil's in the toilet right now. Okay, that's why gas is 92 cents. I never thought I'd ever see gas 92 cents again. I don't think it's been 92 cents as long as you guys have been alive. Okay, it's like the lowest ever. It's sweet. It's not good. I know that it's not good if you're in the oil industry, but I'm not in the oil industry, and I love filling up my big truck for less than $100 when I go there. Okay, so yeah, it all depends on what's available. If you're in a place where, electricity is very expensive, then an electric car is probably not a good idea. Okay? And the other part is electric vehicles, the batteries and stuff, they work well in kind of moderate temperatures, not as good. Like if it was minus 30, you probably wouldn't want to be driving an electric car to work, because when batteries get cold, they don't function as well. Right? I mean, even your car, if you have a gasoline-powered engine, isn't as efficient at minus 30. It'll still run, but it doesn't run as efficiently. Okay. Right. Okay, so we're talking about thermal energy transfer, some energy always being lost to the surroundings. Okay, so you can never come close to getting the energy out of a system that you put into it. Okay, and that was one of the things we had that first day, right? One of the things was, which law was this? You can't even come close, right? I don't know if you guys remember that question. Anyway, so for efficiency, the formula for efficiency is this. Okay, useful work output divided by total work input multiplied by 100. Okay, now what I like to do with this formula is just take the times 100 part out. Right, makes it easier to manipulate. We all know that if I get 0.85, my percentage is 85. We can all kind of do that part in our head. Okay, so I change the formula to this. Okay, efficiency is output work divided by input work. Right, and then you guys can just understand that whatever decimal you get is the percentage. Okay. All right, so to give you some idea here. Automobile internal combustion engine typically runs 12 to 15% efficiency. An electric engine runs up to 95% efficiency. Okay, so yeah, very efficient. All right, problem is for making it mobile, our technology for batteries and cells is not there for the range yet. Okay, it's getting better. Like we have electric cars now that can travel several hundred kilometers before requiring a charge. Okay, but the problem is you drive several hundred kilometers, now you have to stop for a few hours to charge the car. If you're driving a internal combustion engine, you stop, fill up with gas, and in 5 minutes you're driving again. Okay, so it's still practicality. Yes, they're good. Yes, they're efficient as long as you're, going to work and going home and you know that the car can manage that range without being charged. Okay, then you're good. If you're trying to drive across Canada in an electric car, that's probably not the best thing to do. Okay, because you're going to be stopping every, 4 hours at the most. Okay, probably a lot more often than that. Okay, to charge. Right? And then I don't know how long it takes. A few hours at least to charge. Okay, steam reciprocal engine. Okay, well, we don't see many of those anymore, but okay, they run 50 to 75% efficiency. Okay, it's essentially like a turbine. Okay, turbine engines 40%. Okay, so turbines, yeah, they're certainly more efficient than automobile internal combustion because there's less conversions using a turbine than there is here. Okay, the more conversions of energy you have, the less efficient you're going to be. All right, so we're looking at this example here. Okay, crane lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work. Okay, however, it only manages to get 8.0 times 10 to the 3 joules of useful work done. Okay, so we've got it used this much energy. Okay, this was the work that was input, 2.3 times 10 to the 4. Okay, this is the work that was output, 8.0 times 10 to the 3. Okay, the smaller number, like we said, is always going to be the output work. It's always going to be the number that goes on the top. All right, so if I want to calculate the efficiency, okay, the efficiency will be, the work that was output divided by the work that was input. All right, and we have 8,000 divided by 23,000. Is that very efficient? Okay, looking at 34.8% efficiency. What? How did I do that? It's right here. I had it done already. No, I didn't do that calculation in my head. Okay, everybody with me there? Okay, what if I need to manipulate this equation? How would I solve for, let's say, how much energy was required to do a certain amount of work? What would I be solving for then? Work input. Okay, if I want to find out how much work I actually have to do to get this job done, that's this number. How do I solve for that number? No, using this formula, I mean. How would I get this number by itself? Andres? No, because if I do that, I'm going to have 1 over this. Right? I got to move it over by multiplying. Okay, bring it over here, multiply both sides, and then divide both sides by the efficiency. Okay, think about this, guys. Is efficiency always going to be a decimal? Right? Because we're not going to do the multiplying by 100. This would be 0.348, right? So if I divide 8,000 by 0.348, will I get a bigger number? Yeah, when you divide by a decimal, you always get a bigger number. Okay, so that would give me the work input. All right with that? Okay, so for manipulation, that's what we would do. Okay, if I wanted to find the work output, I would multiply these two numbers together. Well, if I take a decimal and multiply it by this number, I'll get a smaller number. Everybody all right with that? Okay. All right, I'm going to give you a worksheet. It's got just a few efficiency problems on it. We'll work through those and see where we're at after that. Okay, so in this one here, obviously you have to do some manipulation of the formula because they give you the efficiency. Now, an efficiency of 15% means that this is our efficiency, agreed? 0.15, right? We have to turn it back into the decimal form. All right, and that's used to do 3.2 times 10 to the 4 joules of useful work. So is that the top number or the bottom number? Top number, right? Okay, so efficiency equals, okay, work output, okay, divided by work input, right? And so we're looking for how much energy had to be supplied in order to do this job. So we're looking for the bottom here. So we multiply both sides by that, and then divide both sides by efficiency. So the work input will be the work out, okay, divided by the efficiency. So that's going to be 32,000, okay, divided by 0.15. Okay, everybody with me there? All right, is the answer on your sheet? No? Oh, that's weird. All right, so we're looking at 32,000, okay, divided by 0.15. Okay, so we're looking at 213,333 joules. Okay, is that making sense? That's the hardest manipulation of that formula, so. Okay, just so that we kind of have an example of all of them. All right, so we have a small electric motor, okay, has an efficiency of 85%, okay, so we know efficiency is 0.85, okay, lifting a small load, it produces 15 joules of mechanical energy input, okay, so we've got our work in is 15 joules. We're looking for how much useful work was done. So efficiency equals work out divided by work in. Okay, we're looking for work out. So we multiply both sides by work in. Okay, that'll give us our work out. All right, so 0.85 times 15 joules. And it's going to give us around 12.5 or something like that. 12.75. Okay, so 12.75 joules would be our useful work output. Okay, everybody good with these? All right. If you're done that sheet, okay, you've got a little bit of time to maybe start getting stuff organized for our review tomorrow. All right, so tomorrow we'll go through. I'll do my usual thing where I outline the key concepts and then talk a bit about what's exactly on the test, and that's your chance to ask some questions. So you might want to look through stuff right now and start thinking about what kind of questions you want to ask tomorrow, okay, so that you have everything together for the weekend to prepare for your test. Okay. Number 8, yep. All right, so on this one here, they tell us the mass and they tell us where it's lifted to. Can I figure out how much energy would be required to do that? Yeah, so I go m times g times h, and that's going to be my work out. Okay, that's how much work I would have to do. All right, so if I do that, then I'll be able to figure out what the input is by going work in equals work out over efficiency. So it'll essentially be 2,000 times 9.81 times 5 divided by 0.35, and that'll give me the work input. Yeah? So that was just combining a potential energy question with an efficiency question. Okay, any other ones there, guys? All right.